So now we go over to the technology that tries to disconnect all remember from the fuel that it put in. If you go to the thermochemical processes, where to produce different renewable hydrocarbons. Our base at Chalmers is the fluidized bed technologies, and which is developed to be extremely fuel flexible, that can take any fuel, more or less everything that is burned can be used for us. In our process, this is an example of this kind of units, and this is the most popular conversion technology for this kind of fuels in the scale that we talk about when we want to do renewable fuels. This is an example from Valmet. It's an 88 megawatt multi-fuel boiler that can burn more or less anything from coal to sewage sludge or waste, all in the same unit. So going to this unit, we can see that it has a fuel feeding system, a reactor where you have the thermal conversion, in this case combustion, as you have the air. You have a convection pass, which is developed quite a lot during the last 20 years to actually handle all kind of fuels, to take down the temperature in a controlled way to avoid clogging of the heat exchangers. You take the temperature down to around 150, 160 degrees. You have the filter take away the particles. Then you have a fan dragging the gas through it. Then you have a flue gas condenser, which is very popular in Sweden, to take out the heat. And then you leave the flue gases in the chimney. This kind of unit, if you look on the efficiency, you usually see that they have an efficiency of like 110%. And that is by the definition of the heating value. And as we have a flue gas condenser, you can take out the heat and you also use it, which is not included in how you calculate the heating value. Now I make it a little problematic for you. I turn this circulated fluidized bed upside down, and then I put on a bubbling bed, fluidized bed up here. Both of these you can think about using a fuel with a very high moisture content, around 50 to 55%, which means that they have a refractory inside of them. And now how should we do then make this become a gasifier or paralyzer? You just place them next to each other. You transport the heat from the fluidized bed reactor to the bubbling bed and the unconverted fuel back to the fluidized bed. And then you have here a gasifier or paralyzer, dependent on which temperature you use. If you use wet fuel here, you don't get so much of gas out. So you need to put a dryer to dry the fuel to make the heat go in, to be used to convert the fuel instead of just boiling water. Further, if you use a system like this, you will plug the heat exchanger within like 40 minutes. So you will plug this in like 40 minutes, so you have to do something. What you do then is that you balance the chemistry. And this is what we have learned with the startup of the Go Biogas unit, how to use the catalyst by the ash from the biomass itself to take it up in the boiler, release it at the catalyst in the gasifier. Then you get the product gas that you can cool down to a temperature around 150 degrees, actually using the same convection path that you use in a regular boiler. The same filter system, and then you have the condenser. In the condenser, you have some polaromatics that you have to feed back. At the present, actually now in the boiler, we actually test active surfaces of the heat exchanger, managing to actually have this as a regular flue gas condenser, but for the product gas instead. This we have shown. These units are up and running. They run for several 100,000 of hours in megawatt scale around the world. At Chalmers, we have our own, the gasifier. It's been operated for more or less 10 years. Operating above 750 degrees, we have gasification, 550 degrees pyrolysis, and if we stage the temperature in the reactor, we can have both pyrolysis and gasification in the same unit. So we can produce the pyrolyzed oil and the hydrogen for the hydration of the unit. It is an extreme efficient process. You put in a chemically bound energy of 100 megawatt, and you get out 102.5. This is the measurement data from the Goodbye gas. If we want to, we can get this up to 106. But of course, you have to put in some heat here. And this is dependent on how you integrate it, how much you get. If you optimize this system for a commercial unit, you get around 81 megawatt as syngas. Charcoal goes to the combustion, and you get your aromatics as products if you build it large enough. The total efficiency around 87% then, based on the chemical energy then. To make something good of the product gas, if you want to have a synthesis process, the chemical route, you can do any chemicals that you do from oil or gas. You need to take away the BTX, the benzene, toluene, and xylene, and then you have to compress it. This is also standard equipment up and running in 1,000 of megawatt scale around the world. The potential of this technology. We can actually build this on existing boilers all around the country. The gray bars here is a circulated fluidized bed in Sweden. Blue is bubbling. If you add a 2 times bigger bubbling bed to your circulated bed, you have an indirect gasifier, the same type as in Goodbye gas. And if you have a bubbling bed, you add a circulating fluidized bed of half the size. Just place it next to them, connect them, and you can operate them. This is the same way that you can change from coal grate-fired to fluidized bed biomass furnaces in the 90s. If you then convert them to gasifiers, they become massive. This is the Värta plant. If you put them together, it's 1,000 megawatt of biomass, a 2,600 megawatt of biomass gasifier. Then you can talk about logistic problematics. What you actually have here is the reason here, around 500 megawatt, or between 2 and 500, which is the regular size that we can look on. And we have around 60 units in Sweden that can be rebuilt for this purpose. Down to around 100 megawatt gas, it's for heterogenic catalyst. If you go for lower scale or smaller scale, we can go to biochemical use of microorganisms to convert to any of these products that we want to. If we do this, the potential, and we say that we rebuild all our units, it will cover a fuel demand of 284 terawatt hour of biomass. That is the need that we want to have. This is a magic number. It corresponds to the energy coming for all refineries and petrochemical industries in the West Coast, or Shell refinery in Rotterdam. This is the amount of fuel that they use. It will produce around 185 terawatt hour of renewable hydrocarbons. The forest growth in Sweden is around 200. This means that we have to have a massive import of biomass if we want to feed this type of system. And this corresponds then, if we do this, we could convert approximately the same amount of carbon dioxide per capita that in average in the global. So regular 8 to 3, if you have a boiler, you can convert it to a gasifier, then you get 270% more conversion capacity. If you look on the utilization of our boilers in the industry today, it means as a chemical converter, we usually use them around 8 to 10%. And no other industry equipment, you invest in like 1 billion crowns, you use like 10% of the capacity. So here you have a big opportunity. It also have a big opportunity for the electricity. If you add electricity to the boiler for heating, you have a marginal efficiency of about 100% as you remove the flue gas losses. You can have hydrogen into the electrolysis, and you can convert CO2 to hydrocarbons. The potential, if we use the full potential as we saw before, we can add 350 to 460 terawatt electricity to the system, producing 410 to 450 terawatt renewable fuels from the same. So this is a big opportunity to use the infrastructure we have and the sites we have.